We have a visitor.
We have multiple visitors.
Wait a minute.
We have Seagull. I don't know why they maybe I thought you guys were watching.
See. You're not like the others. Are you here usually? Okay. Okay. Welcome to Linear Algebra. I will begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for the students. Just ask you to bless our class today, Lord. In your name I pray. Amen. So we are talking about what today? Math, right? Yeah. Linear transformations. Hey, somebody looked at the course planner. Woohoo! Are you watching my video? Did I say that in the video? Oh, I made some horrible pun in an announcement, didn't I? Oh, man. I have the juice, but I don't have the shirt. Somebody left their scarf, though. What do you think? Yeah? Yeah? What do you think? Should I do it?
No, that's on camera. Wait, do it. Please do it. Please do it. It's probably like Morgan's or something.
It's probably Morgan's.
Please.
You guys are mean. All right.
You
You give me a cookie if I do it. I would take bribes in cold hard cash, thank you. And or Star Wars Legos. No, I give you cookies and or ice cream on near assessment near.
Domino's gift card with like $8 on it.
If there is cookie or ice cream anytime near course evaluations, that is merely coincidental. It has nothing to do with trying to influence you. Although, in case I forget, let us remember in course evaluations, strongly disagree is worth more to a professor than not applicable. Marking not applicable is stronger than strongly disagreeing. If you really want to hurt a professor's course evaluations, not applicable, not applicable, not applicable, not applicable, not applicable. That is a 0 out of 5. The strongly disagree is merely 1. That's still something. Not applicable. If you really want to hurt me, not applicable, not applicable, not applicable. Don't do that though.
I know what's worse than not applicable.
What's worse than not applicable?
Top hat.
Top hat. Ah, you monster.
He wrote it on his hand.
You got me. All right, linear transformations. Definition. A function, t, from v to w, where v and w are vector spaces over a field f, all right, is a linear transformation and we also use the terminology linear map or linear operator, all right? But linear transformation if the following two properties hold. Number 1, t of x plus y is equal to t of x plus t of y for all x and y in the vector space V. And 2, that t of c times x is equal to c times t of x for all constants in the field, all scalars, and for all x and v. So just as a point of terminology, let's agree that this first item we'll refer to as additivity. And the second one we'll call homogeneity. But, I mean, side comment, there is a larger sense in which homogeneity is used. And technically, this is like homogeneous of degree 1 or something. That doesn't matter. Let's just say it's homogeneous, okay? I mean, that means, or if you want to be less fancy sounding, you can say you can pull scalars out. All right, that's 2. We can pull scalars out, like so. These two things together make a function a linear transformation. All right. Furthermore, because we like to give a name to where things live, right? T is an element of linear transform. I think I used a script EL, like a script EL, linear transformations from V to W. I should mention, if you read more sophisticated mathematics books, this is sometimes called HOM, F sub F VW, which means it's a homomorphism from V to W with respect to the field F. But anyway, we will use, that's just a side comment, guys. We're going to use this, okay? If T is a mapping from V to V, and T is an element of LVV, well, in that case, we'll just say we have a special name for this. This is called just L of V, or as also as popular notation, endomorphisms of V. End V. Let's see here. There's a, continuing with my litany of unnecessarily duplicated notation, this is also known as GLV. Little GLV. Big GLV is something different, all right? So such a thing is called a linear transformation quote unquote on V, all right? AKA an endomorphism of V. All right. Enough jibber jabber? Yes, I think so. Let's work out a property of a linear transformation. Fundamental theorem. If T is a linear transformation from V to W, then T of 0 is equal to 0. All right? So let's prove it. Check it out. T of 0 plus 0 equals to what? Yeah, T of 0. But that says that T of 0 plus T of 0 is equal to T of 0, right? Hence, by cancellation, which we proved is true for what? For any vector space, right? We get that T of 0 is equal to 0. So the first property, I mean, a very important property anyway of linear transformation is that it maps 0 to 0. Okay? Another important property of a linear transformation is, well, I don't know if this is that important, but not surprisingly, if we had T of a finite linear combination, right? I equals 1 to Cn of Ci Vi, what would we get? I mean, if you can do it for a sum of two things in one scalar multiple, you can extend it to finitely many of these put together, right? So by repeated application of part 1 and 2 here, we have the sum I equals 1 to n of Ci T of Vi, right? Let me restate this result as a theorem. If I'll say if V is the sum I equals 1 to n of Ci Vi. Let me use a different letter than V. Let's say that's, what do you guys want? How about X, right? If X is a linear combination of V1 through Vn, then what? Then T of X is what? can I put this into words? If x is a linear combination of v1 through vn, then t of x is a linear combination of t of v1 through t of vn, right? I mean, this is an element of the span of what? T of v1, t of v2, t of vn, yeah? And by assumption, where was x? X was an element of the span of what? I could express what I'm expressing in this theorem right now using the image of a set notation. Do you guys know about function? Like, what does it mean? If I have a function, right, and it goes from, say, a to b, right, and if I have like a1 is a subset of a, and I look at f of a1, what's that equal to? First of all, it's the image of a set, which is again a set, right? And that's just like, what is it? It's f of x such that what? Where's x coming from? X is in a1. This is called, so this is the so-called image of a1 under f. So if we know about this notation, like images of a set under a function, we can restate this theorem using spans and images. What is this? How could I restate this theorem in terms of span in this notation? T of the span of v1 vn is equal to what? It's equal to the span of t of v1 t of vn. So in other words, a linear transformation takes a span to a span. And in kind of the most natural way possible, right? You start with a generating set v1 through vn, and the generating set for the image is just the set of images of the generators, namely t of v1 through t of vn. Okay, enough about this. I probably should show you some examples, right? What are some examples of linear transformation? How about t of f of x equals to df dx, where f is a function from the reals to the reals, and let's say f is an element of C, how's it go, C1R. This is my notation for once continuously differentiable functions. That means you can take one derivative, and the resulting derivative is itself a continuous function. Is that a subspace? I mean, first of all, is C1R a vector space? I mean, I would point out that this is a subspace of the function space from reals to reals, right? Because if you take the sum of two continuously differentiable functions, you get a continuously differentiable function. And if you take a scalar multiple of a differentiable function, you get a differentiable function. And is it non-empty? Well, take a constant function, like the function that's always equal to 0, right? If you differentiate that, what do you get? You get the function which is always equal to 0, right? So that function's in there. So by the subspace test theorem, C1R is a vector space, a vector subspace of FRR. FAR. And so this is a linear transformation, right, on this vector space. Right? Because why? Well, do I need to write it out? I mean, the derivative has properties 1 and 2, right? With respect to here, x and y are not x and y, right? They're what? Like f of x and g of x, right? The inputs are functions. I guess I probably should write that out. So we have to interpret the definition appropriately to the context, right? But everybody here, I think, has had calculus 1, right? You guys who are visitors, are you taking Calculus 1? So you know that if you have the derivative of a sum, you've got the sum of the derivatives, right? And here, that would be t of f of x plus t of g of x. And can you pull scalars out? I mean, we know this, right? This is a property of differentiation. If I put a constant here, it puts it here, and of course I can pull that out. I should make a remark, right? If we can show that t of cx, let me use, instead of using x, let me use v, t of cv plus w is equal to ct of v plus t of w for all c in the scalars and v and w in the vector space, then that suffices to prove that t is an element of the linear transformations from v to w, right? If we can check, what I'm trying to say is we can check additivity and we can check homogeneity in one foul sweeping calculation, right? Does that make sense, what I'm saying here? This is related to the fact that when we're checking something's a subspace, we could check closure under addition and scalar multiplication at the same time, right? If we just look at cx plus y, whether that's in w again, if x and y are in w. Because we can do what? We can put c equal to 1, that gives us the additivity, right? And we could put what? We could put w equal to 0, that gives us the homogeneity. Because why? Theorem 1 says that t of 0 is 0, right? So I know that t of 0, if I put w equals 0 is 0. So I recover both 1 and 2 by checking this. All right, next example. How about t of f of x equals to, I don't know, the 133rd derivative of f. Is that linear? If I take the second derivative of a sum of two functions, it is the sum of the second derivatives of the function, right? That's also true for third, fourth, fifth, sixth, 133rd derivatives. Not that you've taken too many of them, but why not? All right. Now, in this context, of course, my vector space would not just be once differentiable functions. I would be maybe looking at functions which can be differentiated 133 times. But in fact, I'll look at t as a mapping from smooth functions to smooth functions. What's a smooth function? Right. It means infinitely differentiable. That means if you can take the kth derivative, you can also calculate the k plus 1th derivative of that by just differentiating it, and that resulting function is continuous. So it has infinitely many derivatives, all of which are continuous in their own right. Smooth functions. Again, a vector space because we can check the subspace test.
We mean non-trivial derivatives, though, right?
What's that?
We mean non-trivial derivatives, though, right?
Non-trivial derivatives. What do you mean by that?
So would the zero function then be smooth by that definition?
Yes, the zero function smooth.
Okay.
Yeah. Constant functions, polynomial functions, exponentials, sines, cosines, cosh, sinh, products, powers, sums of these. Careful with division. If you divide by 0, that gets you into trouble. Right? Dividing by 0 will chop our domain back from R to something else. But anyway, I'm starting to get away from linear algebra at this point. But you could do other things, right? You could look at t is equal to like d squared minus 3d plus 2, where this is t of f equals to like f prime prime minus 3f prime plus 2 times f. This is a linear operator. We study this in differential equations. All right? So, and that's, in fact, a linear transformation again. All right, these are all examples on infinite dimensional vector spaces because function space is not finite dimensional, right? You asked me what's the basis. I can't tell you because you can't write a basis for function space, all right? So my fourth example is much friendlier, which is something like this. Let's see here. How about this? T of x comma y equals to x plus y, comma 3x minus y. So this is going to be, I should tell you the domain, from R2 to R2. Oh, by the way, in terms of function examples, we could have also done what? Like definite integral, I think would work, right? Because the integral of a sum is the sum of the integrals, and you can pull constants out. How about limits? Limit has linearity. Oh, I forgot to mention, if we take 1 and 2 collectively, this is known as linearity. What I've circled in green is just checking linearity of t. Linearity is both 1 and 2 combined, okay? Linearity. So almost everything you look at in calculus is a linear transformation, all right? Usually we'd say that these are linear operators because they take functions to functions. That's when the word operator is used. The derivative is a linear operator. Is this function, my example 4, is this linear? I mean, you could sort through it, but let me show you the lazier way to do it. Rewrite this as T of V equals to what matrix times V? Where V is equal to xy. I got a 1, I got a 1, I got a 3, I got a negative 1. Right. In other words, we could write this as AV, right? And let me put it over here so everybody can see it. So for continuing 4, if we have T of V plus W, oh, I should check linearity, right? Be lazier, right? Do it all at once. T of CV plus W. T of CV plus W, I can write that as what? The matrix A, which is what you guys told me, 1, 1, 3, minus 1. But let's write it like A, because writing those numbers does not give me joy. A times CV plus W, right? I should say, let V and W be where? Elements of what? Yeah. I take your real numbers, and can somebody add something to that for me? R2, right? And now C is a real number. So the inputs for the linear transformation and for our vectors, two-dimensional vectors, right? And so, hey, but this is a matrix vector product, and we have already spent considerable time proving facts about these things, right? We know that we can pull constant out of matrix vector multiplication, and we have this distributive property, right? And so that's what? That's C, T of V, plus T of W, which proves what? It proves that T is linear. That's right. So that is a linear transformation.
Are affine functions generally linear?
Good question. I'll come back to your question in just a second. I'm going to take a theorem related to example 4. If we have T going from, say, in fact, Fn to Fm, and A is in Fm by n, such that T of x is equal to Ax for each x in Fn, then T is an element of the linear transformations going from Fn to Fm. In other words, if you can take your function and write its formula by a matrix multiplication, that proves it's linear. The proof of that is what we just went through in example 4. I mean, there's nothing really special about that being a 2 by 2 matrix, is there? Or it being real. The calculation I did over there on the lower square corner proves this theorem. Right? Now, so that's just piggyback theorem here on example 5. Daniel's asking me, what about a linear function? Is it linear? So, I mean, in other words, if we have y equals mx plus b, right? If that's equal to f of x, is f linear? Is f a linear function? Right? In the sense, is it a linear transformation, if you will, right? I'm tired of writing transformation. Map. There. What do you guys think? It shouldn't be additive. Well, what was the theorem I had written here before but erased? What was the third thing I told you about a linear transformation that's always true? Beyond the definition, is that t of 0 is what? 0. What is f of 0 here? F of 0 is equal to b. So this equal to 0 is a necessary detail. A necessary, well, let's say fact for linearity of f. In other words, no, a linear function is not a linear map unless what? Unless b is 0. So in other words, it has to be the graph of a line that goes through the what? Through the origin. So technically speaking, this is what's called an affine function. More generally speaking, definition, if you have a t mapping from, say, a vector space V to a vector space W, and t of x is equal to, oh goodness, how does it go? Well, like p plus s of x. I'm not sure what off the cuff, I'm not sure how to define this. Very careful. This is my, I don't usually try to define this. It kind of caught me off guard here. If I write t of x is equal to p plus s of x, where s is linear from v to w, all right, then t is affine. Is it a affine transformation? If that p is 0, then it's just linear. But affine is like a constant in the sense of a vector, like a vector constant plus a linear function. All right, well, anyway, we don't talk too much about those, but it's Nathaniel's fault. So let's see here. Can you guys tell me any other examples of linear maps? Any ideas? Here's another one that's important to differential equations. You take the Laplace transform of f of t. It defines a function of s. This is by definition the integral from 0 to infinity of e to the minus st f of t dt. And this is linear transformation for f of t suitably bounded. In other words, there's a set of functions for which this integral converges, and you can prove that set of functions is in fact a vector space, and so this would be a linear transformation from that vector space to a new vector space of functions of s. Electrical engineers call this changing from the time domain to the frequency domain. But this is, again, a linear transformation because it's built from an integral, which is linear. So, yeah, matrix multiplication, but there's a wild world of, there's all kinds of interesting linear transformations. One other thing I would add, so finally a non-example, right? here's some non-examples, actually. If we had t of xy equal to like x squared y squared, that wouldn't work out well for us. If we had f of x equals to x squared, again, not linear. Can you guys give me some more examples of nonlinear functions? How about t of a matrix is equal to a matrix squared? Would that be linear? I mean, all of these are. Oh yeah, these. I think these actually are all homogeneous degree 2. That is true. But I think these all fall from the same problem. Like t of a plus b is what? A plus b squared, which is what? It's not a squared plus b squared, and it's also not a squared plus 2ab plus b squared, because what? I said a was a what? Matrix, and we know matrices don't commute, so this gives us like a squared plus ab plus ba plus b squared. So that would be like t of a plus t of b plus this garbage. Right? So it is not additive. It's also not homogeneous, right? If I pulled a constant times a matrix, I'd pull out the constant squared in this rule. So there are tons and tons of things which are not linear. I would also make a comment that calculus 1 is actually all about linearizing, in some sense, a function, right? Like the derivative is what? It's the slope of the tangent line, right? So there's some kind of linear function attached to any function at a point of tangency. We can explore that further. Okay, enough about that. I have one more somewhat abstract example here. I'm sure I have homework problems like this. If we had t, say from Rn by n to Rn by n, with t of a equal to b times a, all right, where b is a square matrix, it's a fixed, I'm fixing a particular b. Does this define a linear transformation? Well, try it out. If I have t of, say, ca1 plus a2, that would be equal to what? So just properties of matrix multiplication, what I gave as the definition for t, there you have it. And it's, in fact, a linear transformation. There are lots of examples of linear transformations. Now, so at this point, I have a couple different things we can talk about, all right? So I'm going to give you guys a choice. Would you like to talk about kernel and image? Or would you like to talk about the converse to the theorem that's on the board?
We
Talk about our feelings.
We have to cover all of them.
Yes, we have to cover all. I'm not asking you guys anymore. So we'll look at the counter example of this. If the other, so this is if then. We're going to explore the start at the, so let t be an element of this guy. I don't know why I gave you guys a guy. Oh, I should. Why did I even open the floor up for discussion? All right, so suppose we have a linear transformation from Fn to Fm. All right, assume that. I'm going to prove that we can write the formula as a matrix multiplication. Here's how it goes. X, an element of, what is it? Fn has x equals to what? The sum. I equals 1 to, let's say j equals 1 to n of x sub j ej, right? So t of x is equal to what? You guys with me? Again, I shouldn't have asked the question. All right. I'm going to erase. Maybe after I'm done erasing, you'll be with me. So what I'm trying to do right now is to show you that if the function is a linear transformation of column vectors, then we can write the formula as a matrix multiplication. Okay? So by linearity, I can pull out the sum and I can pull out the constants. Right? But then, what are we looking at here? Let me rewrite it this way: x1 t of e1 plus x2 t of e2 plus da 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 plus xn t of en. So by the column, by how do we say a matrix times a vector is what? A linear combination of the columns of the matrix with coefficients taken from the vector. In other words, this is a matrix column vector product. What is the matrix? What is the column vector? Here's the column vector, x1, x2, xn. What's the matrix? The first column is t of e1. The second column is t of e2, and so forth. The nth column is t of en. And there you have it. That proves that if we have a linear transformation of column vectors, we can write the formula as a matrix multiplication times the column vector. This matrix I just wrote down and derived for you is so important it has a name. This is the so-called standard matrix for T. Right? And so the notation for that is just this, bracket T, close bracket X. So if we have a linear transformation, we can write it as the standard matrix times a column vector. Can we do this? What kind of linear transformation? It's not just any old linear transformation. The ones I just erased over there, most of them no, because they're on infinite dimensional vector spaces. Or the matrix example, that's a finite dimensional case, but there's no, like, you can't do this on that example either, right? We're going to actually have to sort through coordinate maps to make sense of that later. So this is the so-called standard matrix. Let's look at an example. If I have T of, say, xy equal to x plus 2y plus 3z. Oh, where'd the z come from? Oops. 4x plus 5y, and then 6z down here. Ooh, I keep trying to put z back in here. There's no z. This is equal to what? One, 2, 4, 5, 0, 6. We'll go with 0, 6. And so the point is that this right here is the standard matrix of T. Now, you could also calculate that as T of E1, T of E2. If you wanted to go that way, you could do that. What's T of E1? 1, 0. T of what was it? 0, 1. And if you put in the formula, T of 1, 0 is what? 1, 4, 6. And what's T of 0, 2. Put in y equals 1, x equal to 0, you get 2, 5, 6. And I obviously should have put 0 on the first one because x equals to 0 gives me, x equal to 1 gives me 1, 4, and there's 0 here at y equals 0. So, and of course it's the same. So this is the standard matrix of a linear transformation. Usually you guys are very, very happy when I put this as a test question. Like, please, we'd like lots of these, right? So, yeah. All right, so next up, let's see here. Special subspaces connected to T mapping from V to W linear. So first of all, the kernel of T is equal to x in V such that T of x is equal to 0. So the kernel of T is the set of all inputs which map to 0. Now, in terms of functions, this is actually the inverse image of the set just containing 0. So, I mean, technically speaking, this is the fiber of the map over 0. If you don't know that language, then okay. You probably don't. That's okay. Also, image of T, sometimes called range of T. All right. This is T of V. All right, so in particular, the image of T is T of x such that x is in V. I said these are subspaces. What's the theorem here? Kernel is a subspace of what? Kernel of T is a subspace of what? Image of T is a subspace of what? T. T is a mapping. It's not a vector space. You tried? Okay. V, right? Kernel is a subspace of the domain. And the range, of course, is a subspace of the codomain, so W. How would we prove this theorem? Let me do it. Should I take your test for you? Why did I even ask that? Tell you what, you just give me $300. I'm going to buy a really nice laser printer and some really fancy cardstock. I will make a certificate that says that you know linear algebra. It's gonna. It'll look glorious. We'll put it behind glass.
I can do a $100 down payment right now.
What's a DCP? Let's see here. So the proof. I don't know why I start this. All right, that's cheap. Yeah. Wait a minute. Well, a straighter line. More or less this idea, right? I mean, I don't know. So proof. If x and y are in kernel T and C is in the field, then T of Cx plus y equals to what? Well, yes, but I lost you at $300. Let's see here. T of y, but we said x and y are in the kernel, which means T of x is 0, T of y is 0. So this is equal to 0. Therefore, Cx plus y is in the club, the kernel club, kernel of T. And T of, what did you say? Do they have fried chicken? So we should check that the kernel of T is non-empty, right? T of 0 is 0. That means 0 is in the kernel of T, right? So it's what? It's a subspace by the subspace test, right? How would we prove that the image of T is a subspace of W? Let's let x and y be in the image of T. All right. And I think I've been using T of W for, I can't remember what my notation is commonly in the notes at the moment. I'm sorry, guys. I didn't have a chance to remind myself of my name calling. So let x and y be in the image. All right. I'll just put everything up here. Right? One of them's got to be right. And C be a scalar, then there exist A and B in V such that what? Such that T of A is equal to X and T of B is equal to Y, right? By definition of image. All right? This is what it means to be in the image. It means that there's something in the domain which maps to it. Okay, so consider T of CA plus B is what? Yeah? Oh, okay. C T of A plus T of B. But what was T of A by construction? X, and T of B by construction was Y. So we have Cx plus Y. And what does this calculation show? Thus, therefore, Cx plus Y is in the club. It's in the image. Because I've just showed that Ca plus B maps to Cx plus Y, right? Which is what we need. We need something in the domain which maps to the alleged thing in the image, namely Cx plus Y. I've shown that. Therefore, Cx plus Y is in the image. We'd be done, except what do we need to know? We need to know that the image is non-empty. Why is the image non-empty? Remember the third thing we know about a linear transformation? T of 0 is equal to? 0. Where is that 0 in the range? That's the 0 in W, right? So therefore, the image is a subspace of W. Finally, I buried the thing. What I wanted to say at the start of today, but math meetings always get me off kilter. Part of the reason I showed you guys in the snow day what I did about about coordinate map is why. What is a coordinate map? First and foremost, it is a linear transformation. That's what Proposition 2 said in the Wednesday video, right? Coordinate map is a linear transformation. It is the most important linear transformation in this course in some sense. So we'll talk more about that next time and the more general idea of what is an isomorphism. All right? So, thanks, guys.
Is the solution of initiative on Blackboard?
It should be.